Let me move on to the main topic here. The presentation title is Parametric Study of Non-Periodic and Hybrid All-Stick Bending Active Gridshells. First of all, I explain the background of this study. The roof covering a space that accommodates a large number of people is called a spatial structure, and it protects the space from external effects such as seismic motion to ensure the safety of people. Traditionally, to construct an architectural roof with a dome-like shape, masonry, latch shell, or continuous shell has been applied. But masonry and latch shell, respectively, are composed of small bricks and short trusses, which tend to lead head assembly process. A continuous shell requires many formworks. Formworks are often used to temporarily dispose of after construction is completed. It is not environmentally friendly. To overcome the problem, all-stick bending active gridshell can be a useful tool. It reduces construction time and cost, because the curved surface is generated from an initial flat grid composed of flexible beams. A curved surface of ABAG is obtained by simple out-of-plane deformation without any formworks. In addition, all-stick bending active gridshell has no hinge joints, so small number of parts are needed. As for this point, it is quite different from a conventional bending active gridshell composed of beams and hinge joints. Other advantages of the bending active structures in general are its lightweight, which makes it easy to transport, and once the initial flat plane is generated, it can be reused in various forms. Two major attempts have been made so far to design this structure. The first one is a parametric study to get an idea of the basic mechanical properties of ABAG. The second is to tune the distribution of Gaussian curvature on the surface after large deformation by continuously changing the shape of the units. Our study is greatly inspired by these two works. The purpose of this study is to propose an easy shape design method for an ABAG. To achieve it, I introduced an evaluation method over a discrete curved surface of an ABAG. In addition, simple uniform patterns composing an ABAG have the limitations on the shape of a deformed surface. So I introduced design method of initial flat grids with non-uniform patterns. All-stick structures for inplane deformation shrink in one direction when they are composed of the orthogonal direction. Conversely, they expand when they are stretched. This extraordinary deformation is caused by the negative Poisson's ratio of the structure. They are composed of REENTRANT units, whose shapes are repetitive and concave. One of the specific properties of all-stick structures is that dome-like shape can be easily obtained by out-of-plane deformation due to negative Poisson's ratio. We showed the method for shape design of a new type of architectural roof by taking the advantages of the property. Design parameters of the REENTRANT units are sizes W and D in X and Y direction respectively, and angles theta between blue piecewise linear elements and X-axis. We use the two types of REENTRANT units, REENTRANT honeycomb and REENTRANT quadrilateral. These units have negative Poisson's ratio and composed of two types of members, chevron rods and tie rods. A chevron rod has continuous zigzag shape, and it can bend and twist elastically under large deformation. By contrast, a tie rod is assigned discretely and connects two neighboring chevron rods. Since the ABAG is modeled as a discrete frame structure, it is effective to evaluate the amount of convexity and concavity of the curved surface of the ABAG as a discrete quantity without resort to a continuous parametric model of the surface. It leads to avoid higher order differentiation of geometrical properties. Here, we introduce the discrete Gaussian curvature defined in discrete differential geometry. Discrete curvatures compute the curvatures at node on a polyhedral surface. First, triangles based on nodal positions of discrete members of ABAG are needed for computing the discrete curvatures. For simplicity, nodes are assumed to be located on the connections between chevron rod and tie rods. Circular marks represent nodes on the connections. On the other hand, triangular max represent ones on the additional nodes, which are defined as the average of the position vectors of their neighboring 4 nodes. Gray areas represent hexagonal cones on each node composed of 4 triangles. Hexagonal cones are generated for all nodes except those on the boundary. Discrete Gaussian curvature is defined for computing the amount of convexity and concavity on a polyhedral surface. It is formulated as an angled effect from a flat shape. This formulation is represented by only intrinsic quantity. We obtain a cone for Kp is larger than 0. If Kp is 0, a flat plane, a cylinder, or a cone is generated. In the last case, a saddle shape is obtained. Here, we show examples of curved surfaces and distributions of the discrete Gaussian curvatures on them. They are composed of single uniform reentrant units. The contours of surfaces represent the heights of nodes. Their discrete Gaussian curvatures have simple and symmetric distributions. Simple uniform reentrant patterns are useful to design initial flat grids of ABAGs, but a uniform pattern can only generate a simple and symmetric shape of a curved surface, as shown in the previous slide. To overcome the limitation, we utilize various shapes and arrangements of the reentrant units in an initial flat grid. Here, we introduce the 2 types of ABAGs, non-periodic and hybrid ones. First, non-periodic one is assigned shape parameters gamma to an initial flat grid with subdomains separated by y-direction lines. The initial flat grid of a non-periodic one can be generated by tuning the value double of each reentrant unit multiplied by shape parameters gamma. Second, a hybrid ABAG is composed of the 2 different reentrant units. The type of reentrant unit is defined based on the geometrical relationships of chevron rods. The signs of theta I and theta I plus 1 define the geometrical relationships between the ith and I plus 1 chevron rods. If the product of theta I plus 1 is negative, then reentrant honeycombs are generated the corresponding chevron rods. Otherwise, we obtain the reentrant quadrilateral between them. In addition, the mixed method is important because we can easily obtain more complex and asymmetric freeform surfaces of ABAG than those with a single uniform unit. In this study, we use GFRP, glass fiber reinforced polymer, as material of members. The cross-sectional height and width of all members are constant. The sizes of units are shown here. The normal angle theta is pi over 6. This is an initial flat grid of an ABAG. All the mechanical examples have the same boundary conditions. Shape of the boundary of an ABAG is a rectangle in the initial state of large deformation analysis. The both ends of chevron rods are roller supported, which can move along the x-axis. All connections between tie rods and the chevron rods on the boundaries are also roller supported, which can move on xy plane. Both displacements of 0.30 meters are assigned at both ends of chevron rods. The arrows indicate the directions of the force displacements. To generate a curved surface, large deformation analysis is carried out using ABACUS 2018. First, we apply the virtual upper load equal to the self-weight to all members before assigning force displacements. It enables us to avoid numerical difficulties due to an unfavorable bifurcation backlink. Then, force displacements along the x-axis are given at both ends of all chevron rods. The self-weight is removed after the first horizontal displacement is completed. Here is an example of an ABAG surface composed of non-uniform units, where the contours in the xy plane show the values of the discrete Gaussian curvature. Non-periodic ABAGs generate surfaces that are symmetric with respect to a plane parallel to the xz plane. And the discrete Gaussian curvature increases where the shape parameters gamma is smaller than the surrounding area. On the other hand, hybrid ones are symmetrical in the plane parallel to the YZ plane, and the shape of the generated surface and the distribution of the discrete curvature are different between these two cases. In the top model, RH and RQ are arranged alternately. On the other hand, in the bottom one, the distribution of RH and RQ is divided into two layers. In addition, the mixed type of non-periodic and hybrid generates more complex discrete Gaussian curvature distribution. Designing the initial fat grids of ABAG using the proposed method is considered to be effective to obtain various surfaces. The shape design method will also combine active gridshells with non-uniform reentrant units, which generate more complex shapes than those with a single uniform unit. This Gaussian curvature is used for quantitatively evaluate curvatures at nodes on an ABAG. In the numerical examples, we showed the various shapes of ABAGs. This is the end of my presentation. Thank you for your attention.